Hello and welcome to another tutorial. So this time we are going to be taking a look at an AI technique known as behavior trees. So we're going to be setting up a basic system for creating behavior trees. So let's dive on in and look at sort of the project that we're working in. So this project might be a little bit familiar. It is the project that has the GOAP, the goal-oriented action planning based AI in it. And I've kept that GOAP AI in here. And what I'm going to be doing is setting up the behavior tree AI alongside that. So in terms of the difference between the two, so with GOAP, we have our goals, those have a priority, and then we have actions, and there might be one or more actions that try to achieve those goals. Whereas with behavior trees, what we have is it's organized in a tree structure. It's organized as we have different sequences of actions that it will try and do, and it has different ways in which it tries to evaluate those. So the sort of classic nodes that we have in the tree as our building blocks is we have selectors. So what a selector will do is it will try and run one of its children. If that succeeds, then it doesn't run any of the others. If it fails, then it tries to run the next one. And it does that till it goes through all of the children. So a selector only fails if all of its children fail. So a selector is really handy for having something where it's a case of, okay, we'll try doing this. If you can't do that, here's this other thing to try. If you can't do that, here's this other thing to try. The other sort of foundational node we have is what's called a sequence. So a sequence is where it will try and run something. If that succeeds, then it runs the next child. If that succeeds, then it runs the next child. So a sequence only succeeds when it has successfully run all of the children. If any of them fail, it will stop running. So how we can start to build things up with this is generally at a fairly high level, we'll have a selector, and then that will have different things that it can try and do. So in this project, what the AI previously would do is it would wander around. Otherwise, it would try and chase the player if it detected them. So in this case, that chase would be the first sort of node that it's going to try and run. So we'd have a selector, and first child is going to be the branch that does the chasing. Second branch is going to be the wandering. So if it can chase, it will always do that. If it can't, then it will wander. Similarly, things like of the wander, we could break that up if we wanted to into multiple stages, multiple things that it tries to do. So that's sort of the foundation for what we're going to be getting set up with this. Now, there's going to be a few differences to sort of classic structures you might have seen for behavior trees, and I'll talk about that when we get to those of why I've done those. So these are definitely inspired a bit by the setup that Unreal uses for their behavior trees, which works really, really effectively. So, okay, let's get a few things up and running. Okay, so our first step is there's a bunch of classes, things like that we need to get set up. So what I'm going to do is the structure-wise, I'm going to have our actual behavior tree, and this is going to be more of a wrapper container for it. So this is going to be the one that is mono behavior based, and it's going to handle sort of holding all of the information there for it. Then we're going to have our individual nodes. So I'm going to create a separate folder for this. And there's a few different nodes I'm going to create. One of the things is I want to have a base node class. So I'm going to have a node base, and it's actually going to have most of our logic in it. It's going to be the one that has the most set up for it. Then I'm going to create one for our main types. So we're going to have our sequence. That's one of our building block types. We're going to also have ones, obviously, for things like selector. So we'll set that up as well. BT node selector. And we want to be able to run particular branches if a condition is true. Now, for now, I'm going to do that as its own dedicated node. In future, I want to actually change that so that it functions a little bit more like the Unreal ones, where it's something we can attach onto a node. But for now, we want to keep the setup, avoiding it getting too complex and too intricate. So then we also have our final one, which is one that it just performs an action that does a particular thing. So, okay, that's our various node classes. Now I'm going to open those up, and I'm going to open up the behavior tree one as well. So we're starting to get quite a few classes here. So that's good. What I'm also going to do is I'm going to set up the script that will actually sit on the AI for performing the particular behaviors. So with our GOAP one, we handled that by we were just adding on the individual components. What I'm going to do is I'm going to create a script here that is going to be BT setup. Now this would be something that would be per AI. So we would actually, on each AI, set this up differently. But for now, I'm going to add in the behavior tree. I'm going to add in the setup script. And then we can now start getting this built up. So there's a bunch of things we're going to need to be able to be doing. And what I'm going to do as a starting point is get a little bit of things in this behavior tree one. This is our one that wraps around all of our stuff. So it's the one that handles pretty much all of the main logic. So this is going to have in it our actual BT node base. So this is going to be our root node for the behavior tree. So I'm going to make it a property like that. I want to be able to say it's a new BT node and give it a name. Now I'm writing code that is going to have errors at the moment. That's intentional because I want to get a little bit of stuff defined of how I want these interfaces to work before I actually implement those. So I've mentioned before, this is an approach I like to go for with this, where I will write the code for how I want to use it before I actually write the implementation. We're going to do that with this as well. So I'll actually be writing the code to create the behavior trees before I write the code to actually execute them. So inside this is where I'm actually going to define when we execute, when we do things with our nodes, being able to define what they return back. And this is one of the key things that I'm borrowing from Unreal, is this idea of normally in a behavior tree and in sort of classic implementations, you see a node has either succeeded or has failed. There's never a concept of a node being in progress. So nodes don't have any of their own information, and that really can make a big impact on performance-wise. It means you're always evaluating the full tree every time. It means that it can be a lot harder to debug, and behavior trees in general can be a bit harder to debug because if they are rapidly flickering between states, between nodes, that can be really hard to track down. So we're going to add in this in progress state. And that's going to be the key that allows us to have this be a bit more efficient. So in start, I want to be able to reset the behavior tree. So again, a function that does not yet exist, but that's okay. In update, I want to be able to tick the behavior tree. And I'm going to actually pass in the delta time, just in case we wanted to actually do anything fancy with it. So, okay, that's our behavior tree class, our BT setup one here. So this is going to require that there needs to be a behavior tree attached to this. So we're going to require that component. Again, this would be something that would be per AI type. We would generally have this set up. So type of behavior tree, just so it's mandating that. And then we're going to set up stuff for being able to keep track of some key things. So for our AIs, well, we need the behavior tree. We're going to need access to the actual AI agent. We're going to also need access to the sensors, so our awareness system. What we're going to do is just retrieve all of those. So agent, get component. So with all of these, that's all we need to do to be actually retrieving those. Linked behavior tree, can retrieve that as well. And then finally, we do the same thing with the sensors. Good, we've retrieved all of those. Now I'll actually change that to, I want to do that in wake. We actually won't have anything for start or update. Then what I want to be able to do is I want to be able to actually set up the behavior tree. So I want to get that root node. So linked behavior tree, root node. And then I'm going to be starting to add things to it. And these are actually going to be heavily based upon the existing behaviors. So I want to have this based upon, for example, things like our wander and our chase behavior. So if I take a look and grab our wander one to begin with, so the priority side of things, I don't need to worry about. The action side of things, I do need to worry about. So this search range, I'm going to bring that over. Set that up here. So we're going to have header, wander settings. I might actually change that to be wander search range, or just even wander range. So, okay, let's set up the wander node in terms of the logic. So if we think about with the behavior trees, how I want this to work is that there can be something that happens the first time we enter a node, and that I want there to also be something that can happen every time we tick that node. So we want this concept of an enter function and a tick function. That mirrors what we have with our actions here, where we have enter that does particular action, and then we have our ticking. So I want to be able to do something like of that. Now in terms of how I want this to be set up, okay, I want to be able to do something like this, or I can say wander root. I want to be able to go, okay, well, BT root, I want to add a BT node sequence. And I'm going to call this wander. And then how I want to be able to use this is then I want to be able to say wander root, add an action node, and then the action node is going to be perform wander. And I want to be able to define a couple of functions for it. So the first one is going to do exactly this. So it's going to pick a location, start to move to that, and then it's going to say return and it'll return behavior tree, our enode status, and our in progress. Then the other action is going to be the on tick one. So what this is going to be doing is checking, okay, well, if the agent is at the destination, then our behavior tree node status is succeeded. Otherwise, it's in progress. So that looks pretty good for our logic for the behavior tree. Now, that didn't update that. That should have, there we go. That's better. So we wanted to be able to add in the action, have it perform the particular logic. That looks pretty good. We might need to, with this, specifically go BT node action, but we'll find out. Once we've got all of these set up, we'll start to implement the logic and start to implement the interfaces. So this is enough for me to actually start implementing things. I will set up the chase one after I've got the wander working, but I want to get the basic logic happening now for this. And there's quite a bit to it. As I said, the base class here is where we're going to put most of our logic. So firstly, this isn't based on mono behavior. So it doesn't have a start and update. What it does have is a name, and we want to be able to easily retrieve that. For that name, we'll make it a protected set, and we'll default that to no name, just so it's clear. Now, any node could have children. So we want to have a protected list of those children. So they will be a protected list of node bases like that. We do want to initialize that. And I'm going to, I think that's fine. We don't need it to be accessible publicly, so I'm not going to make it a property. Now I want to be able to have the logic that it can run when it enters and when also it's being ticked. So the ideal thing for that is, again, protected, a system func. So system func is something that can return a value and can also take parameters. A system action can take parameters but can't return a value, but using system.func allows us to have one that can do both. Now in our case, it actually only needs to retrieve or be able to return that node status. So this is our onEnter function, and then we'll have the exact same thing for our onTick function. That looks good. I'm intentionally not initializing them so they will be null by default. Now the other thing I'm going to do, and this one I will have as a public property, behavior tree, node status, and this will be the last status. Public get a protected set, and we will default that to unknown. So that looks good. So, okay, so far so good. Now we're going to need a constructor here for our node base, and this is going to need to be able to take in a name. It's going to need to be able to take in a system func, a node status, on enter function. It's going to need to be able to do the exact same thing for our onTick function. It's good. We've got those. Now we will default those to a null because those we want everything essentially to be optional. So we can set all of these on into function and do the same with the onTick one. That's good so far. We've got those set up. Now we do have our add functions here that we had in our BT setup. So we want to get these so that they are actually working correctly. So what we can do is if we go to our node base, one thing we need is a public BT node base add, and we're going to make this a generic function. So again, it can be given, actually we won't make the name optional in this case, but we will say where T has to be a BT node base and where it is newable. The reason being is I need to be able to go new node is new T like that. I need to be able to set the name, which I'm going to actually bring the name here. So it's optional. So I need to be able to do that. Now I can't directly go and actually set that name. So I need to be setting it this method. Actually be new node. Yes, we can't actually pass the name into the constructor there, unfortunately, so that's just something to be aware of. But we can add this, and then we return new node. So it's good. We create the node, add it to the children. So let's see how BT setup is going error-wise. So we're still getting a couple of errors. That's to be expected. We haven't set things like our sequence and that to be based on node base yet. So we're going to do that for all of these. BT node base, we get rid of start and update. So we're going to do that just with all of them. And the goal is we're trying to get to the point where our BT setup is compiling. That's good. We've got all of those updated. So let's see how BT setup is going here. So that's better. Now we can see it's saying no overloaded version takes 3 arguments. Now that's easy enough. We can set up this so that we also support these functions. Now again, we have to manually be providing these in like this. Good. Got those. So we can save that. So now we can see BT setup. That's largely working. Or search range, we need to fix that to wander range. So it's good. No errors happening with this. So there might be other things that we do need to set up with this. What would be helpful is also to have a function where we can just provide it an already completed node. So another BT node base, add T, and it takes in new node. Again, we provide the where T is BT node base. And then similar logic to what we did here. What we could actually then do is this. We could do a return add new node. Just so everything's going through, similar paths. So that's good. We can add the node. Now we've got other functions that won't be working yet. So in our behavior tree, this reset is not going to be doing anything. So the idea behind reset is it takes the behavior tree and clears it back to a known state. So reset, I'm going to implement now. So this one, I'm going to make it virtual because there might be things where a child does want to override it and do additional logic, things like that. So what this is going to do is set the last status to unknown, and then go over all of the children and do the reset on them as well. So that's all reset needs to do. Just takes everything, sets it back to the last, so that everything is at that unknown status. So that's good. Now we have our tick function, and tick is where there's going to be a fair bit of logic happening. So there's quite a bit that needs to happen in tick. So firstly, we're going to have our tick. Now this is intentionally not going to be virtual. So delta time. So what I want to be able to do with this is I want to attempt to tick. And if I haven't managed to tick anything, so essentially if nothing has done any work, then that means we've fully evaluated the behavior tree, and I want to then reset it. So we restart back over again. A classic implementation of a behavior tree essentially runs and then resets every time, whereas we're only going to reset when we need to. So what I'm going to do is bool ticked any nodes. I want to have on tick, and I want to then provide that delta time. And then f, we did not tick any nodes. And what I want to do is do a reset. So no actions were performed, reset and start over. That'll allow things like our wander to run, keep running until it finishes, till it gets to the goal, and then reset and start picking a new location once it's gotten there. So it looks good. Now we have our protected virtual bool on tick delta time. So, okay, this is one that's a little bit more involved. And this is actually really the core of the behavior tree is in this. Once we've implemented this, we'll actually have most of the logic there for it. So firstly, I want to keep track of if we've ticked in nodes, and we'll return that so it's no longer grumpy at us. At this point, we should have no compile errors. And we'll go back to Unity and just check. So we do have one here because we had an extra brace. So just good to double check that there's no errors happening. And we're clear of errors, so that's good. So, okay, we're coming into this. First thing I want to do is check, is this node's last status unknown? Because that's going to tell us that we've never entered this node. So are we entering this node for the first time? If our last status is unknown, then what we want to do is we want to have an onEnter that gets run, because it's got to do a little bit of logic. That is going to be another protected virtual. That will be that. So what this is going to do is our onEnter, if we actually have one of those onEnter functions defined, we want to run it. So, and it should be updating this last status regardless. So if we have an onEnter function, so if onEnter function is not equal to null, then this is equal to the result of invoking that function. Otherwise, we need to check if we've got children. So this is where it starts to get a little bit complicated. So what I would actually do is break this up a little bit. This is a case where using the ternary expressions, it starts to get a little bit messy. So it actually, in this case, to last status, that. So that then what I can do here is I do still end up using a ternary one, because if this has children, then we are in progress, because one of the children could be executing. So our last status ends up being, check if we've got children. If we do, then it's in progress. Otherwise, we've succeeded. So the logic here is that if we have a onEnter function, we go and update the status at that point, because that could completely run and have done everything that it needs to at that point. Otherwise, if we have children, we don't really know whether we've succeeded or failed yet. So we set ourselves to in progress, and then that status we can update it when we go and actually evaluate the children. Otherwise, we know we've succeeded because there is no further logic to happen. Again, that could be overridden further down here, which is fine. So onEnter ran, so we did tick nodes this time. So, okay, we know we've entered the node. Now we need to check, do we have an actual tick function for the node? So is there a tick function defined? So if our onTick function is not null, then, okay, our last status should be based upon invoking that. So it lets that update that status. Again, ticked any nodes is true because we have done work. Now, if that last status is anything other than in progress, we're done. Even if we have children, because if it's succeeded, we don't go and evaluate those child nodes if we have this. So we don't support having a action node having children. So what I would be doing is if the last status is anything other than in progress, then we return that ticked any nodes. So if we succeeded or failed, then exit. So okay, we've handled a couple of simple cases. We want to now, okay, so we don't know, if we've gotten to this point, then we might have handled any entry, we might have handled running any tick logic. What if there's no children? Well, that's something that we should handle as well, because we might as well exit at that point. So if children.count is 0, if our onTick function is null, then we automatically say that we succeeded. And we return if we ticked any nodes. So the logic here being, if there is no children and we don't have an onTick function, then we're done. We've succeeded. It's evaluated everything it could. Essentially, this could only happen if there's an empty node placed there. It's just a bit of a safety net there for it. So that's good. We're earlying out in that scenario. So now we actually handle ticking the children. Okay, so we can now have the tick barrel on down through the children. So what we're going to do for that is obviously loop over all of the children. And then again, what we need to be doing here is if this child is already saying that it's in progress, so if its last status is in progress, then what we do is ticked any nodes, we'll do an or equals with child on tick delta time, and we just return ticked any nodes. So if it's already in progress, then we don't actually change anything. So we just keep running that node. So if the child is in progress, then only out the ticking. So that's good. So if the node, then at this point, already we know we've handled in progress once. If the node hasn't actually been ticked, if the node has actually already been ticked, so it's not in the unknown status. So if it is not unknown, then that means it's either succeeded or failed already, which means we can ignore it. So we ignore if the node result has already been recorded. Otherwise, if we get down to here, we know that the node status must be unknown, which is fine, because if we run at when it's unknown, it'll do the onEnter logic, things like that. So what we can do is we can actually go then and we'll say ticked any nodes and same logic. So we run that tick behavior and our last status becomes equal to our child's last status. So we just inherit that status from them by default. So inherit child's status by default. So that's good. Otherwise, we need to do some particular things depending upon the status. This is to facilitate being able to do things like our sequence and selection ones, for example. So if our child's last status is in progress, then we can just return ticked any nodes. Otherwise, if the child failed, so if it failed, well, we need to allow the node to control if it should continue evaluating if that child failed. So so in this case, what we'll say is if we are not allowed to continue evaluating if child failed. So if that's the case, then what we do is our status will already be set to failed. So we just do a return ticked any nodes. And then the final one we have is if the child succeeded. So if they succeeded, and we shouldn't continue evaluating if the child succeeded, which will support the selector nodes. So this is for our sequence nodes, and this is for our selector ones. So continue evaluating if child succeeded. So if we're not allowed to be doing that, well, we're already set to success because we've updated the status here. So we return ticked any nodes. So that looks good. That handles our different particular ones. So I'm going to set up these functions now. So protected virtual bool. That, and we'll, by default for these, what we're going to do is we're just going to return true. So default behavior is going to be we just always continue running. Have the same thing for succeeded. So what that means is for our sequence and selector nodes, all we actually need to do for those is we need to override these functions to a large extent. So we have this, we have a protected override, like that. Now for sequence, we do not continue evaluating if a child failed. So for sequence, we return false in this case. And we go to selector, and then it continues evaluating if the child failed. Now it continues evaluating if the child failed, but not if it succeeded. So that's good. We've got most of what we need for our sequence and selector nodes there. So then if we go to our base one, we're largely done, but okay, what if we've gotten through and we've evaluated all of the children? I want to actually specifically handle that because there is different behavior that we might need to have happen, much like we have these ones here. So I'm going to have a protected void onTicked all children, because in the case of a sequence node, if we have successfully ticked all children, then we want to actually check, did that final child succeed? If it did, then we have succeeded. So we want to have a protected override void onTicked all children. Saved so that it can pick it up. So, okay, we know, and we need to mark this as virtual. So we know we've ticked all of the children. We want to check if the last one succeeded. So essentially our status is determined by whatever the last child was. So what we would be doing is we'd be saying our last status is equal to, we want to access the last child. The easiest way to do that is we do _1. Now that will access that last one. So we use their status. Now for the selector, we want to actually do a similar thing. So we'll bring this same function over to the selector. Because if the last node succeeded, then it should return success. If the last node failed, it should be marked as failed. So it's actually the same in both cases. So that's good. We've got our sequence and selector ones set up. We've got then largely everything we need for our base node here. We've got our logic for resetting things. So that looks pretty good. Be nice to have the ability to debug this and be able to see a bit of information about what's happening. So I'm going to set up some debugging first. So we're going to have a script here, bt debug UI. Now I've already set up a little bit of UI here for debugging the behavior trees. So what I'm going to do is bring that over to this, and we're going to set this up. So this is going to use TextMesh Pro. We're going to make it that we just actually have to manually link up the behavior tree that it's referring to for the behavior tree to debug. And our TextMesh Pro UGUI. That's our linked debug text. So by default, we'll just actually clear that out. So maybe string like that, and then in update, I want to be able to go, hey, link debug text, and I want to be able to say linked bt get debug text, which we don't have any function for that yet, but that's okay, because that is what we're going to implement next before we go and get things set up in terms of being able to do the rest of the bits. We're going to get this function implemented. So it's going to be a public string get debug text, and that's going to return root node get debug text. Essentially following the approach of implement the logic so that we get errors until we've actually completed the implementation. So again, we have a public string get debug text. Now, because we're going to be assembling quite a bit of this text, what I'm going to do is use a string builder, debug text builder. Just makes it a little bit more efficient if we're building a bunch of stuff. So I want to go get debug text internal, and we provide that. And then at the end of this, we'll do that. So now I can have a protected virtual void, get debug text internal. That takes our string builder like that. Just makes it a bit easier to actually work with. Now, I also want to be able to give an indent level, because what I want is this to be progressively indented so we can see what parts of the tree are what. So I'm going to have indent level. I'm just going to have as be 0. So then apply the indent is the first thing we do. So for our index is 0, and do that. And not the most efficient way of doing it, but it gets some basic stuff happening there for the indent. Then I can put in the actual thing, info for the node. So I want to add in the node's name and then the node's status. So last status to string, like that. So that's good. Then for each child, what I want to do is run, firstly, debug text builder append line. So we put things on a new line, and then child get debug text internal and indent level +1. That's all I really need to do for this. So this should be enough that if I link all of these things up, that I can actually see it run the wander tree and I see it move around. That's really what I'm aiming to be able to see with this. Make sure we save everything. So let's find out. We should see our behavior tree appear here, which we do. We can see it's in progress. It's performing a wander. And we're going to go and check and see where our AI is. I've definitely moved. Yep, they've definitely wandered far away. So what I'll do is I will actually switch to our scene view for this, so we can see where they are. So we can see them here. They've moved to a location. You can see the path that they're following. So they are wandering between different locations, which is good. If I gave them a much larger search range, so let's increase that to 50, they'll head much, much farther away. But we have the basics there working. So that's excellent. Now we're going to go a little bit more complex with this, and we are going to get our chase behavior happening. So the chase one is a little bit more involved. So if we take a look at our chase action and goal, let's take a look at what needs to be happening here. So firstly, whether it can run or not. has a much more intricate set of logics. This is where we need our condition one. So we haven't actually implemented our condition logic yet, but this is where we're going to need that condition one. So what I'm going to do is I'm actually going to take this whole set, and we will redesign this a little bit, but we are able to use this as a base. I won't actually delete it. And we're going to go over here to our setup. So first thing I'm going to do is bt root. I'm going to add in, so similar to what we did with this, I'm going to have chase root is behavior tree root. Let's add in a condition node. Now in this case, I'm going to actually provide the constructor for it, and chase, and it's going to be a similar setup where we have to provide a function. It's going to be a little bit different in terms of how that function works. But chase root is going to need to return true or false essentially. So if we have no targets, well, it's easy, we return false. So, okay, this is checking if the current target is still sensed. So if it's the detectable one is that, and the awareness is greater than, so essentially it should still be detecting it, we return true. So we're still aware enough of the target that we should run. Otherwise, we search for the target until we've found a particular one. And then if we have, with this, I'm going to actually make it that we search for the one with the highest awareness. So that is going to be the min awareness to chase, which we don't have that variable over yet. So we have variables we need to transfer over, that's fine. So if this is greater than that, we'll do that. Candidate.awareness. So that's good. And then here, we just return current target is not equal to null. Now this is a bunch of variables we then need to set up from our chase here. So things like our awareness to chase and the target. We need to bring those over. So we're going to have header chase settings. So we're again going to rename these a little bit. If that looks good, we can rename this here in each of the cases, just so we're using the correct one. Good. And then this needs to be chase underscore, and same thing here. So that actually looks pretty good for the condition. It's able to return true or false. Now we need to set up so that we have the actual proper way of initializing that condition node, which I can get rid of that. So what I will do is for condition, it's going to need a protected system func that returns a bool, and this is our condition function. We need to also keep track of if we were previously able to run. We'll see why in a moment. Run. So that can be false. So then we need our constructor for it. So this needs to be able to take in, firstly, a name, and it needs to be able to take in a system function, like that. Now, what this is going to need to do is, you can run the base one to set up the name like that. We're going to store a condition function like that. Okay, we've stored the condition function. I'm going to set up a thing to actually evaluate that and give us back a behavior tree node status. And we'll see why in a moment. Evaluate condition. And what that's going to do is, firstly, can run is our condition function invoke. Now, we should check if that condition function is actually set, just in case. So if the condition function is not equal to null, it's that. Otherwise, it cannot run. And then if we can run, then we return saying we're in progress. Otherwise, we failed. Now, if we switched from being able to run to not, or vice versa, there could be data stored in a particular node or action that needs to be reset. So this is why if can run is not equal to was previously able to run, what I want to do is I want to go and reset all of the children. Just to ensure that they are in the correct state. And we store the values like that. So it's good. So we can go back to our setup one. And so our setup one's now happy. The other thing I'm going to do here is our root is actually going to be a selector, like that. Now we're going to provide it with a name. So we will say that that is base logic. Reason being, we want a selector there so that the chase one can run if possible. If it doesn't, it runs the wander one. So that looks good. We've got our condition node set up. And our chase, we've set up the condition for it. Now we can set up the actual action, which if you look at the action for chase, there's not really much to it. It's moving to that target. So we can grab that. And then our chase root, we add BT node action. And what that is going to be is, so our action node, we need to give it our different functions. So this is going to be chase target. Now action, we haven't given it any additional logic. And so far we haven't really needed to. That's something where if we wanted to, we certainly could. So this is going to be, we return in progress. And this is moving towards our target's transform position. Looks good. And we actually use the exact same logic for the tick function. Never actually needs to succeed because it is perpetually chasing them. We could have a distance that it checks, but we don't absolutely need to have that. So we've set up our chase logic here. We have one final thing we need to do in the condition, because we've set up our evaluate condition function, but we haven't actually run it. So we need to have our onEnter function link to evaluate condition, and our onTick function also link to evaluate condition, just so that it's actually running those. So we can now go to test this, and I've expanded the scene view here to make it a little bit easier, so I can hide from the AI. So we can see at the moment, can chase is failing, it's wandering. Now it's seen me, but it hasn't detected me enough to decide that it wants to chase me. Now it has. So you can see it's running that chase logic. So now if I manage to hopefully successfully hide from it, and I need to hide from it for a bit, it will actually lose sight of me, and we'll see the wander behavior kick back in. So I've managed to get far enough away that it will be losing detection of me, hopefully. You can see the chase is still in progress, but now it's switched back to wander. And it's just going to wander randomly around the environment. So we have our basic behavior tree setup working. We're able to add in different conditions and things like that. Now, admittedly, at the moment, we're having to set that up via code, but this is something where future things that we want to look at is adding in Visual Editor, starting to bring in some of the other concepts that Unreal has in their behavior trees, like decorators and services, which are really, really handy. Start to bring in things also like the AI blackboard. So some of our data here, we can just be storing directly in that blackboard. But we've got our basic behavior tree set up, and we've made it so that it's a little bit more efficient. It's not resetting everything every time, it's only resetting it when it needs to. And we've also got core components there of our selector and sequence and some easy ways of being able to add those in. So dive on in and check it out. If there's additional things you'd like to be seeing in the behavior tree one, chuck in a comment below. There's further things I want to be doing with this. Definitely things like a visual editor, definitely things like the decorators and services from the Unreal side. But if there's particular things you would like to see, then do let me know in the comments below. Thanks folks, hope you found the video interesting and helpful. If you have, chuck in a like and subscribe, really helps out, it's really appreciated. If you have any questions, chuck in a comment below. If you're looking for the code for the project, the code is available up on GitHub. You can use the code in any of your own projects, commercial or non-commercial ones. And if you are trying to track down other videos, I do have a searchable video archive, which there is a link to that in the description. And finally, if you're looking for other ways to support the channel, then I do have a Patreon, and there's a link to that in the description below as well. But until next time,